let's calculate the T statistic. I'm going to do it first with the unpooled, and then I'll do the pool, because I did say in this case that I'm not going to, that I am going to pool, but let's start with a slightly simpler one. So what are we doing here? I'm pointing out to you that you can calculate the T statistic from summary statistics. If you know some basic quantities that summarize your data set, you don't always need a computer to do a t-test. That's what I'm trying to underline for you here. So the T statistic is equal to the difference in means between two groups. And if I'm not pooling, that's divided by the sample variance in one group, divided by the sample size in that group, plus the sample variance in the other group, divided by the sample size in that group. And I have all these things for this data set, right? So let me subtract from counties who have more than 50% of people wearing masks, and then I'll subtract from that counties with fewer than 50% of people always wearing masks. So I'm just looking at the means that I showed you previously. So I've got 6.4 here, I'm rounding because why write lots of digits, minus 5.2, the difference in means, divided by, and then I need the sample variances, that's what I calculated. So I've got 3.6 divided by 1533 plus 2.6 divided by 1587. And so if you plug that into a calculator, what you get with this rounding I did here is a T statistic of 19. Okay. Before I talk about that T statistic, let's just do it again with pooling. So to get the pooled T statistic, we're going to need the pooled sample variance. And remember that the pooled sample variance comes from having a numerator, which is equal to the sum of square differences from each group. But that means what we essentially want to do is we want to think about this quantity. This quantity is the sum of square differences in the X group divided by sample size in the X group minus 1. And this quantity is sum of square differences in the Y group divided by sample size in the Y group minus 1. So we want to get the numerator from this first thing plus the numerator from the second thing. Well, we know how to do that. So we can do this more generally first. The sample variance in the X group times what the denominator of that quantity would have been. So this whole thing here is just getting back out the numerator of the sample variance, plus same thing for the other group. So that's the numerator from the sample variance in the Y group. Okay. And then we have this denominator. So actually, you can calculate the pooled T statistic as well if all we give you is the two sample sizes, the two sample means, and the two sample variances. So I can actually do this here. So I've got 3.6 times 1532 plus 2.6 times 1586 divided by 1533 plus 1587 minus 2. And when I do that, I get 3.1. Okay. All right, so now I can go ahead and get my pooled T statistic. So it's still x bar minus y bar divided by, and now I've got my SP squared out here times 1 over nx plus 1 over ny because I got to factor that out. So I still have 6.4 minus 5.2 divided by, this time 3.1. Now note the sample sizes are kind of similar. They're approximately the same in these two groups. So this 3.1 is pretty much in between the 3.6 and the 2.6 as it should be. Okay, so I've got 3.1 times the quantity 1 over 1533 plus 1 over 1587. So I should get a really similar answer in this case, and I do. I get 19.1 with my rounding. Okay. So that's my T statistic under either case. No, the one I think we're doing here, I think we should be pooling here. Sometimes students ask me, why would we ever pool, right? Why not just always not pool since we have the choice? That's a good point. When I do a t-test, I usually wouldn't pool. So why are we even talking about this? Why do we even introduce the pooled T statistic? The reason is that as we get into slightly more complicated methods like regression and ANOVA, for example, those methods turn out to be a generalization of the pooled t-test. Those methods, regression and ANOVA, turn out to assume equal variance, assume the equivalent of equal variance. So when we get to those more complex methods, we won't have this option just to say, oh, we won't pool. So at this moment, even though usually when we do just a t-test, I wouldn't pool because why bother? it's important for us to understand this pooled sample variance and to understand this pooled t-test, because that's the one that's going to get generalized to the more complex cases. So to do the t-test, what we have to do is compare our test statistic, whichever one we're using, to a reference distribution. Now you guys know that technically we should be comparing it to a t-distribution. But you also know that a t-distribution looks more and more like a normal distribution as the sample size gets bigger. Now my view here is that if you have a sample size so small that the t-distribution is not really like a normal distribution, then you shouldn't be doing a t-test at all. Go do a randomization or permutation test. Why bother with a t-test if your sample size is so small that the central limit theorem doesn't really hold, or that the t is not really like a normal? Why bother? There's no reason to do a t-test. Go back and do the randomization or permutation test. You know how to do that, so just do it. So for that reason, I would say you need to just compare the t-statistic to a normal distribution. Now, of course, when you do a t-test in R, it'll get you the precise value from a t, but it'll always be approximately the same as what you would get if you were comparing the test statistic to a normal distribution. And also, since we're not going to make strict up or down decisions based on whether our p-values are above or below some arbitrary cutoff like 0.05, it doesn't matter too much whether we compare this value to a t-distribution or a normal distribution. Let's draw a picture of the standard normal distribution, because that's the one that the t becomes. Okay. So standard normal distribution is centered at 0 and it has variance 1, which means it has standard deviation 1. And 95% of the time it's between -2 and 2, right? And 99% of the time it's between -3 and 3. Now what was our test statistic again? It was 19. Whoa, that's way out here, right? You can't even see my hand reaching all the way out to 19. So what is the probability that we would see a test statistic of 19 when the null hypothesis is true?